My name's Al Averill. I'm with the USDA's Natural Resources Conservation Service. The NRCS helps people conserve soil resources and improve water quality by helping them implement conservation practices primarily on farmland. The NRCS also has a responsibility to inventory and the nation's soil resources and provide information about it. I work as a soil scientist for the NRCS. I'm the state soil scientist for Massachusetts and Vermont. And what I'm going to do today is try to help Envirothon folks prepare for the Envirothon and cover the soils topic and what folks need to know to be able to do well on that topic. Soils, we can't grow without them. That's very true. It's soils are where we get our food. Soils are where we get fiber to clothe us. Soils are very important, and also in that we use soils to put buildings on, to put our playgrounds on, our athletic fields, our homes, our septic systems, et cetera, et cetera. There's a real strong affinity between soils and land, and understand the soils, you can make better decisions about land use. So I hope you'll see that's the case as we go through this process. When preparing for the Envirothon, there are some key concepts, and these are listed in your student manual, the one that is available to you that is provided by the Envirothon Committee and has all the subject matters, including soils. And if you focus on these key concepts, you'll be well prepared for the Envirothon, for the soils part anyway. So you need to look at the section on soil formation. There's quite a bit of information about parent material, which is very important. We'll talk about that at great length. And horizonation, the layers that form within the soil. Soil properties, such as the amount of rock fragments, texture, consistence, structure, and depth, etc. By depth, we mean depth to an impermeable layer, or depth to a high water table, or depth to bedrock. You can imagine that has an effect on how the soil or the suitability and the limitations for the soil for various land uses. Soil-water relationships and drainage class. We'll talk about that at great length as well, so you'll understand what that is. Now, you can looking at these different images of soil profiles. You can see those horizontal layers that we call horizons. You can see different colors, different types of layers, different amounts of rock fragments. You can see that there's a lot of different characteristics just based on these pictures alone, and you're not even able to look at things that are three-dimensional or that you can feel with your hands, the texture of the soil, how dense the soil is, that sort of thing. A lot of different soil properties, and each property has huge ranges that can result in lots of different soil types with varying characteristics. But it's important to understand that from the perspective of wise land use and the capability and limitations of land for that land use. We're going to talk about parent material quite a bit here. Parent material is one of the 5 soil forming factors. The others being organisms, climate, topography, and time. Parent material is the stuff from which the soil developed. And I try to make a point of saying here that it is not to be confused with lithology. Lithology refers to the type of bedrock. Lithology is the study of bedrock. A very small percentage of the soils on the planet form directly from the underlying bedrock. Most of the soils on the planet were formed from transported material. So it's important to understand that. Why is parent material important? It influences a lot of different characteristics and a lot of the different behaviors of the soil, such as weatherability, how readily that material breaks down into smaller components or weathers out chemically. The texture of the soil, how coarse is it, how fine is it? The chemistry of the soil. Does it have a high pH? Does it have a low pH? Is there a limestone influence within that parent material? permeability, the density, the bulk density of the soil, and the pore space throughout the soil affects how readily water and air move through the soil. The size, the amount, and shape of rock fragments, etc. So parent material is very important. I'm going to start by talking about the parent material of Massachusetts. And you see here an image of a glacier. And what I'd like you to take away from this is, please note that the glacial ice is full of stuff. It's carrying material and encroached over the land and picked up material, rocks and soil and boulders, and wore down mountains and hillsides, and has sort of not only a bulldozer effect, but also the ability to sort of pick up material as it encroached across the landscape. So this is not the kind of ice that you pick off the edge of the glacier and put in your beverage. This has a lot of material in it, and all of that material was deposited in one way, shape, or form. One of the ways it was deposited was right at the base of the ice. We call that lodgement or subglacial till. Till is material that is deposited from the glacial ice by the simple force of gravity. It falls out of the ice. Some of it fell out at the base of the ice, where it's compressed and shaped and compacted. Some of it fell off of the edge of the ice, and we'll talk about that. So there's two different types of till that you need to know about. One of them is this lodgement or subglacial till. It's also known as basal till. You'll see that in the literature as well, although that term is considered out of vogue. But lodgement and subglacial, just as the names imply, this is material that was deposited at the base of the glacier. And you can probably see the shape of the material as that glacial ice retreats, forming and shaping the material at the base of the ice. Interesting, in this picture, there's also these pockets of standing water. That'd be a different type of deposition over the glacial till in those pockets of water. And we'll talk about that too. This lodgement or subglacial till has very distinctive characteristics. All tills are poorly sorted, meaning that they have a lot of small material in it and a lot of big material all mixed together. Remember, think about it. This was all mixed up in the glacial ice and then deposited. So it's poorly sorted. There's a lot of different fragment sizes and particle sizes all mixed together. It's very dense, tends to be highly compacted. It has a high bulk density. This is the glacial till that you see here, and when it's encountered by roots or water, it tends to slow roots and water down. It can be actually impenetrable by roots, and of course, water will stand above that dense layer. Not all tills are dark like this. This is reflective of the lithology of the area. The ice picked up that material that was fairly locally and dumped it out locally. So in this particular case, this is down in either the Boston Basin or down around Narragansett Bay, where the bedrock types are quite dark in color. And then you get these erratics once in a while, granite and gneiss. But that's typical. It's a fairly, again, poorly sorted, mixed up material. It's usually loamy, but not always. Now, we'll talk about what loamy means in a minute here. It refers to the texture, and I'll get into it a little bit more. But it tends to be not real high in clay and not real sandy, although sometimes it is. But generally, it tends to be a loamy material. I said that it was fairly dense. It has a very firm consistence, and I just want to step back for a second here and talk about what we mean by consistence. Consistence is essentially the rupture resistance of the soil. How much force can the soil withstand before it breaks up? It's often referred to as the degree of cohesion and adhesion in the soil material. And again, its resistance to deformation. So dense lodgement tills tends to have a very firm, firm or extremely firm consistence. So if I talk about consistence as we go through this process of learning about the soils, that's what I'm talking about. And there's different terms for this. You don't need to know all of these terms for the Envirothon. I only point this out because when we say that the consistency is very firm or extremely firm, it actually, that term equates to a quantified value. But we describe it as things like moderate force between the fingers in order to break the material. The texture of the soil. Again, I know I started talking about paramaterial here, but I don't feel like I can throw out all terms that folks aren't familiar with until I define them. So what is texture? Texture is the relative amounts of sand, silt, and clay, what we refer to as the fine earth particles in the soil, sand, silt, and clay. And the different proportions of the sand, silt, and clay result in various texture classes. And depending on how much clay there is, how much silt there is, how much sand there is in the soil, will have a huge effect on how the soil behaves. So let's talk about that a little bit. Sands are the largest particle size in soil. And when I say it's the largest, that refers to anything that's smaller than 2 millimeters. Anything larger than 2 millimeters in diameter, we refer to as a gravel. And once it gets bigger, we refer to it as a cobble and then a stone and so forth and so on. But when we're talking about soil texture, we're referring to what we call the fine earth fraction. And so that's everything 2 millimeters and smaller. So the largest sand particle, if you can imagine this, if we had a scale here, this would be 2 millimeters across. You can see that a silt particle is quite small and a clay is just a tiny dot. So a silt particle, a medium-sized silt particle, will fit in your fingerprint. And you can see an individual silt particle with say like a 10 magnified hand lens. But a clay particle, you can only see with an electron microscope. And each one of these things, sand, silt, and clay, have specific characteristics or properties. And how do you know if the soil is high in sand? Well, it's very, you can imagine, it's coarse, it's gritty, it feels very coarse, and it feels rough. Most folks are familiar with beach sand or the sand that gets spread on the roads in the wintertime. Silt, being smaller, has a very smooth feel. Think of it as feeling like baking flour, dry baking flour. If you put some of that in your hand and you rub it between your finger and your thumb, it'll feel very, very smooth. It actually feels kind of pleasant, actually. And so that's its specific characteristic. And although it's smaller than a sand, it doesn't have the characteristics of the clay, which we'll talk about next. But the silt, when you wet it enough, it pretty much puddles up and it moves very readily. Where a clay, you can add a lot of moisture to it. It'll hold a lot of moisture. It won't get to be sort of plastic or as muddy as a silt will. Clays have very specific properties. They're extremely sticky and very plastic. By that meaning that they will hold their shape. You can put these things, a soil with a high clay content. You can roll it on a table and it gets smaller and smaller and smaller and still hold together. So again, very sticky, very plastic material. Why is texture important? All of these properties. It affects how well water moves into the soil, how well water and air move through the soil, how much water is held in the soil. The cation exchange capacity refers to the exchange of nutrients in the soil. Generally speaking, CEC or cation exchange capacity tends to be greater in soils with higher clay content. So it affects fertility, frost heave potential. Soil that's high in silt tend to hold a lot of water, yet the water will move readily upon freezing. So you tend to have frost heave and potential in soils that are high in silt. There are some clays that have a high shrink swell potential. When they're dry, they shrink. When they're wet, they swell. So that has a huge implication for like dwellings with basements, for example. And the erodibility of the soil is highly affected by the texture of the soil. In general, soils that are high in silt tend to be the most easily eroded because the silts are small and they're not sticky. They tend to detach from one another. And again, because they're small, they'll move readily. So our most erodible soils tend to be those that are high in silt. This is a texture triangle, and it shows the 12 general texture classes that are recognized in the USDA system of soil texture classification. You can see if you look at this, this will you can actually plot what your texture is based on if you have lab data. So, for example, if you have 60% sand and you have 10% clay, that's going to intersect you right here in the middle of sandy loam. And by default, that means you've got 30% silt. I might throw out some generalized terms, and especially talking about parent materials. So if I say this is coarse textured, we're talking about sands and loamy sands, mostly sandier soils. Loamy or silty are sort of the middle of the road with silt loams and sandy loams and fine sandy loams and so forth. And clay textures are those that really do have a higher clay content. You're going to tend to see the word clay in the texture class name. I'm going to point something out here. You'll see that much of the texture triangle is owned by clay. It's the largest one. And the point is that clays are very have a great deal of effect on soil properties. And so it doesn't take much clay to start to see the word clay in the name. In this case here, we're at about 20%, and we're seeing clay, and we get a sandy clay loam. That said, in Massachusetts, probably safe to say that 90% of the soils have less than 10% clay. So our soils tend to be on the coarser side. It's because they're not very old. They haven't been weathering a very long time. And as a result, they tend to be a little bit coarser textures. The textures haven't been breaking down over eons of time, such as in, say, the southeastern part of the state. The southeastern part of the country. It's not glaciated, and where the climate is warm and moist, and the weathering processes has continued for a very long period of time and continually. Here's a profile of a soil that developed in Lodgement till or subglacial till. This is the parent material here. It is fairly dense. It has a very firm consistence that we talked about, very difficult to dig in. And you can actually see it looks a little muddy down here. So that's because water is seeping in on the top of that dense layer and moving down across the open pit. You can see that the rock fragments, that is the chunks of mineral material that is larger than 2 millimeters, we refer to as rock fragments, are angular. They're not rounded. And that becomes important later. You'll see why. Generally, the textures are loamy throughout. They tend to be fine sandy loams and sandy loams, sometimes silt loams. And but again, the important thing to know about these soils is because of the dense layer, it affects land use. It affects the soil-water relationship because this is a very slowly permeable layer. This landform that you see right here is referred to as a drumlin. You can also see that it's shaped like an upside-down canoe, perhaps, or maybe an upside-down spoon. Where you see landforms like this in broad, smooth hillsides, almost always that's got this dense till in it in the soil. Uh, this long axis is the direction to which the glacier receded. Again, perfect, very nice example of a drumlin. And again, where you have broad, smooth hillsides, you almost always have this dense lodgement or subglacial till. So that's one kind of till. So what's the other type of till? It's referred to as ablation or supraglacial. The word supraglacial implies being above the ice or on the edge of the ice. Like the lodgement till, it tends to be very poorly sorted, lots of angular rock fragments. This is the glacial ice, by the way. This is, in this image, this is the glacial ice. You can see how dirty it is. There's some meltwater at the base of that ice, and there's material sliding off of that ice by the force of gravity as the ice breaks up, disintegrates, and melts. So like the lodgement till, it's poorly sorted. It tends to be a little bit coarser textured, a little higher sand content, a little higher gravel content, but again, angular rock fragments. Here's a soil that developed an ablation or supraglacial till. It's a little sandier in the substratum, and it's permeable. So although it's a till, it doesn't have unlike the lodgement till, it doesn't have that dense layer. Other than that, they're the same, which, the till really refers to the mode of deposition, the type of gravity forced deposition. The lodgement versus ablation or superglacial refers to the position on the ice or above the ice or within the ice, as the case may be. Where do you find these things? I often say to Envirothon students and coaches, don't just look at the whole. Don't just look at the HOLE. Look at the WHOLE. Look around you. Where are you in relation to that landform? Lodgement till, ablation till or supraglacial till tends to be on the valley sides of hills. They tend to be not as smooth shaped, and you can see that these contour lines are undulating a bit. Also, you often find ablation till where as a veneer over bedrock controlled areas, where you see lots of convoluted lines on the topographic map like this. It's often indicative of the underlying bedrock, the shape of the underlying bedrock, which is often highly folded. So you get these little knobs and dips and things. There's often a veneer or covering of ablation, also known as supraglacial till, on those types of landscapes. So where you see these kinds of shapes in the upland positions, up on hilltops, that's often indicative of ablation till. Here's another example of where you might want to find this. Again, valley sides and bedrock controlled uplands. Okay, another type of major glacial deposition is referred to as glacial, fluvial, or outwash. As the name implies, this is the material that was deposited from meltwater from the glacial ice. Again, the glacial ice was carrying a lot of material, and a lot of that material was deposited as from meltwater deposition. What's the difference between glacial, fluvial, and outwash material versus till? We said that till was poorly sorted. Glacial fluvial material is well sorted, meaning that you'll see layers of just one particle size, a layer of sand, a layer of gravel, sometimes you see a layer of sand and gravel, but you're going to see material that is well sorted. It's going to be stratified into layers. And that's because of the nature of the source of deposition. When this meltwater was moving fast, it had a high carrying capacity. If it was slowing down, then it lost its carrying capacity. And when that happens, the larger materials that are being carried by that meltwater drop out, and the smaller materials tend to be deposited further downstream. So you get this layering effect. You also have the rock fragments tend to be rounded because they're water worked. And this is all relative. Relatively speaking, they tend to be more rounded. Here's an example of some glacial ice with a lot of stuff in it. And you can see this meltwater forming a tunnel at the base of the ice. And that meltwater is going to deposit this glacial outwash or glacial fluvial material. I like this image because there's a human being standing right here on top of that ice tunnel, wearing orange, it looks like. This is a topographic map of an esker. When those ice tunnels fill in with sand and gravel, it leaves sort of a snake-like, sinewy landform on a slightly higher elevation than the surrounding area. It's called an esker. You see, this is called Esker Park. That's in northeastern Massachusetts. Here's some typical glacial fluvial landforms. They tend to be in valley positions on higher terraces adjacent to major rivers. When I say higher terraces, I mean the terraces above the immediate terrace adjacent to the river. The terrace immediately adjacent to the river tends to have a different deposition, and we'll talk about that. So see, you got a gravel pit here. That should be a clue to you that there may be some glacial fluvial, or also known as outwash, deposition there. This is a delta that formed when meltwater from this valley encountered a glacial lake that had existed here. Material that came in through that valley encountered the still water of the lake. That material got dumped out, and it formed a delta. You can sort of see the shape of the delta here, and this is what that looks like today. Lots of sand and lots of bedding that occurred as material was dumped over the delta, and more material was dumped on top of that. Here's a typical soil that formed in glacial fluvial or glacial outwash deposition. And you can see a layer of gravel here, layer of mostly sand, a layer of coarser material, mostly gravel, layer of sand, again, well sorted material. And if you look at the rock fragments, the cobbles in this, they're relatively rounded compared to what you might find in glacial till. You don't see sharp angles because that material has been rolled and tumbled by meltwater. Coarse textured, highly permeable, and friable material. It's not dense like the Lodgement till. Another type of glacial deposition is what we refer to as glaciolacustrine. We also refer to as glacial-marine. And this is material that was deposited in the still water of glacial lakes. And this is the Connecticut River Valley that we're looking at here. This is Mount Sugarloaf going south in this direction. The entire Connecticut River Valley at one time was inundated with fresh water. It was referred to as Glacial Lake Hitchcock. It wasn't the only one. And this is a map that shows some of the major glacial lakes that occurred in our part of the world during the glaciation. So this is Glacial Lake Hitchcock coming down through Massachusetts. There's also another major glacial lake. Well, I guess I shouldn't say major because it didn't show up on the map, but there was another glacial lake here. So what happens in that environment? Well, the material gets washed in from the surrounding landscapes into the glacial lake or into the glacial marine environment. And I'll just mention the glacial marine environment a little bit here. That is along the coast, and these are still waters along the coast. What had happened was the glaciers were so heavy that they actually compressed the mantle of the earth, causing inundation along the coast. So the same mode of deposition occurs in both a freshwater glacial lacustrine environment and the saltwater glacial marine. The bottom line is during times when the water is turbid and there's a lot of wave action and there's a lot of material washing into the glacial lake, the larger particles will tend to filter down to the bottom of the lake faster than the very small clay particles. It takes a very long time for clay to filter down through or move down through a column of water. Very long time indeed. So here's a close-up of a typical glacial lacustrine deposit. So you see this layer is predominantly clay. This layer is predominantly silt with a little bit of clay. There's silt in both of them, but what happens is the silt's going to filter down first, while the clay remains suspended in the water column. After everything's nice and quiet, the only thing that's left is the clay that is sort of hanging out there in suspension. It very slowly filters to the bottom of the glacial lake. This is the scenario where in Massachusetts, where you're going to tend to find soils high in clay. And this is the only place you're going to tend to find soils that are high in clay in the state of Massachusetts. That's because our glacial lacustrine and glacial marine scenarios are just don't take up much of the landscape. It's very rare that you're going to find rock fragments in this material, right? This is this fine material that washed in from the surrounding watershed into the glacial lake. So you're going to, again, this tends to be a fairly slowly permeable layer as well. Once in a while, you get these thin layers of very fine sand washing in as well, from wave action and whatnot. But predominantly silty clay material. Typical soil formed in glacial lacustrine, again, high silt content, especially in the upper part, underlain by high silt and clay, and you're not going to find any rock fragments. Where do you find this type of stuff? In the low-lying areas where the glacial lakes used to be, or this is a topographic shot of an area in northeastern Massachusetts along the coastal area, where these were marine inlets and estuaries and so forth, where those silts and clays were deposited. These are now high and dry because the glacier retreated and the mantle of the earth actually rebounded, exposing these areas to the terrestrial environment. Whereas in the freshwater lakes, there was an event that actually broke the natural dam that caused the lake to form in the first place, and the lake simply drained. All right, again, glacial lake area in through here. This is actually a shore area where the lake was. You can see a lot of dissected erosional channels through here, and that's because of the high silt content. And you might remember that we said that soils that are high in silt tend to be more readily erodible than others. There's another type of deposit that you should be aware of. Excuse me while I get a drink of water. And that is an Aeolian deposit. Aeolus was the god of wind in the old Greek or Roman mythology, I'm not sure which. And if you can think about or try to imagine a landscape post-glacially before vegetation got a chance to take hold, before um, there was a lot of again vegetation to hold soils in place, and it was a very windy environment, and that's because there was a massive glacial ice to the north, and when you have wind, when you have cold temperatures or air masses encounter warm air masses, you usually get a very uh, unsettled scenario. It's very windy. So in this case, this is what we refer to as an Aeolian mantle. It's a sort of a blanket of soils that are predominantly high in silt or very fine sand, because very fine sand will move as well fairly readily. And in this case, over sands. So this is an Aeolian mantle over glacial outwash or glacial fluvial material. Another type of deposition, and this has nothing to do with the glaciation. This is after the glaciers came and went. And this is the type of deposit that occurs as a result of recurring flooding events. We call this alluvium. And major river, and adjacent to the major river are the terraces that are formed as a result of the meandering of the river over the course of time. When the river floods, it it inundates the adjacent terrace, the floodplain, if you will, and whatever it's carrying gets deposited on that terrace. And what do you think that would be mostly comprised of? We earlier said that it's the silts and the very fine sands that are most readily moved by wind and water. And when there's a flooding event, there's a lot of material that's being carried into that drainage system. It's moving pretty well. It's moving pretty quickly through the main stem. But when the main stem inundates the floodplain, the water slows down, and whatever the water's carrying tends to be dumped out. So that's the alluvium. That's the material from which those soils develop on the floodplains. I want to point out that happens to be the Connecticut River, and you'll see houses and barns and things like that. And you might be wondering, if this is a floodplain, then how come all these buildings are here? These days, there's two things. Over the course of time, the river can cut down deeper into its channel, and it takes more water to cause a flooding event. But mostly, it's because there's been a lot of flood prevention structures along the main tributaries of the Connecticut River to control flooding. So this is what we would refer to as a floodplain that's not active, inactive floodplain. What do the soils look like that form in these floodplains? In this alluvial parent material. Again, they tend to be very high in silts and very fine sands. You tend not to find any rock fragments because that's not going to get carried into the floodplain by a flooding event. And often you're going to see, if you look deep enough and you look closely enough, you might see some subtle changes in the coloration of the soil. So the surface layers in soils tend to be darker. And why is that? Why is the surface layer dark? Because the surface layer often has an enrichment of organic matter, and it's organic matter that causes the soil to be darker, that sort of that dark coffee color. In active floodplains, you might find a lighter horizon, and buried deeper down, you might see darker horizons, such as this one and this one. That's because organic matter, again, builds up along in the upper part of the soil, but in an active floodplain, that material can be buried where there's a flooding event. So That's where you get the sort of an anomaly in the coloration of the soil. This particular soil profile also developed in alluvium, but it's not on an active floodplain. So you don't tend to not, tend to see more typical soil profile development over the course of time. We have the surface layer is dark with a subsoil that may be sort of yellowish brown as a result of weathering, underlain by the relatively unaltered parent material. Where in the world do you find glacial, fluvial? I'm sorry, where in the world do you find alluvium, alluvial parent material? Next to major rivers. The first terrace position, immediately adjacent to major rivers, is where you're going to find these alluvial deposits, and the soils that develop from them. Okay, here's another type of parent material. And this is referred to as organic, and you might recognize this type of landscape here. You see a lot of cattail in this particular situation. This is a swamp. Oh, I'm sorry, it's actually more of a marsh, right? A swamp technically is wooded. So this is a marsh situation. This is a scenario where the soil's in a position in the landscape where it's wet almost all the time, right? All throughout the growing season, all throughout the year, winter through summer and fall, it tends to be very wet. So it's saturated most of the time. And under those conditions, it slows down the decomposition of organic matter. The plant material that builds up on the surface of the soil doesn't break down readily. It doesn't break down because of saturated conditions, saturated anaerobic conditions. The soil is saturated long enough, anaerobic conditions will develop. And under anaerobic conditions, decomposition is very slow. That's because of microorganisms, the decomposers. Under aerobic conditions, the decomposers work quite efficiently. Under anaerobic conditions, they work quite slowly. It requires anaerobic organisms that can thrive under those situations to break material down, but they don't do it as efficiently as aerobic. So, making a short story long here, bottom line is the rate of accumulation of organic material exceeds the rate of decomposition in these scenarios. So you end up with a buildup of organic material. And that is what we refer to as organic soils, and soils that formed in organic parent material. And they look something like this. Thick peat deposits. This is a really good picture of a thick organic soil. It's difficult to get these pictures because usually when you dig in a hole in an organic soil, it's immediately fills with water. So this was a drained area. I believe this was up in Maine, and a place where peat moss is mined. Organic material versus mineral material. Organic material is much different than mineral material, as you can imagine. You have well decomposed organic material and you get it wet and you squeeze it in your hand. It has no strength. It'll squeeze right through your fingers. Whereas mineral material will not do that. Mineral material will bunch together in your hand. If you let organic material dry out, it will tend to stay dark. If you let mineral material dry out, it will tend to get lighter. Those are good ways to kind of figure out the difference between organic and mineral material. This is a typical situation where you're going to find soils that developed in organic parent material. These are the wettest of the wet areas, and we're probably all familiar with these swampy areas. And topographic maps have these little swamp symbols to show folks where these wet areas are. I want to mention another couple of types of parent material, just in case folks end up going to the National Envirothon or the International Envirothon competition. You're going to tend not to find these parent materials in Massachusetts, but one is called Colluvium. This is material that is deposited by the force of gravity from up above. Material loosens up and it falls down, sort of a landslide sort of effect. Colluvium is what we call that material, and you're going to find colluvial soils or soils that develop from colluvium in mountainous areas, but south of the glaciation, generally speaking. There's an argument that colluvium does exist up in the White Mountains, and it probably does, but in Massachusetts, colluvium is not recognized as a parent material. Another type of parent material is residual. That is the material that weathered in place from the underlying bedrock. And over the course of time, if the landscape is stable and there's no glaciers coming and going to mess up this process of soil formation, there are scenarios where the bedrock breaks up as throughout the course of the weathering process, and the soil starts to develop in that weathered material. And that is called residuum. And if you think about it, you think of the idea of residing someplace or forming in place. So if you look at this map, you might see that this sort of magenta pinkish color is the predominant soil, superficial deposition in the state of Massachusetts. And you can see that that's till. The green is the outwash or glacial fluvial, and that falls along major rivers, right? That sort of makes sense, doesn't it? Major rivers and outwash plains like the Cape. And the purple is the lacustrine material, where Glacial Lake here, you can see where Glacial Lake Hitchcock was in the valley. It was a glacial lake here, a glacial lake here. And the alluvial soils along the major rivers immediately adjacent to the rivers. So you can see that till is the #1 parent material in the state of Massachusetts. It's got a nice pretty map of soil parent material. So I'm going to take a break here and start recording again. And when I come back, we're going to start talking about soil horizonation and the layers that form once that parent material is put into place.